Pips play an important part in the study of radar indicators, and by now you should be able to recognize a pip when you see one. Some are tall, some are short, some are friendly, and some indicate danger ahead. That's the way it is in radar, too. Pips indicate all kinds of things. An enemy task force maneuvering through fog or darkness, our own reconnaissance planes, the splash from a coast artillery shell, the answer to an IFF challenge, or perhaps this is the signal returned from an enemy rocket ship or guided missile. The electronic eye of radar detects and locates these targets. But for this information to be of any value to you, we need different types of oscilloscopes to present this data visually, accurately, and effectively. Some scopes measure range only. Others measure either azimuth or elevation. Some present data on both range and azimuth at the same time. And still others measure both azimuth and elevation. Now you'll see how these scope presentations are formed and how the scopes display the data they obtain. In the first film of this series, we reduced all radar sets into this simplified block diagram. You saw how the timer generates a voltage pulse and sends it along to the transmitter. At the same time, it sends part of each pulse to the indicator, where it starts forming a baseline. Back at the transmitter, the pulse is converted into high-frequency energy, sent to the transmitting antenna and launched into space. However, a spillover of this energy escapes into the receiving antenna and goes down to the indicator, where it appears on the baseline as the main bang. The sweep of the baseline is synchronized with the outgoing pulse, so it can measure the time it takes a pulse to leave the transmitter, reach a target, and its echo return. When the outgoing pulse strikes a target and part of the energy is reflected back to the radar set as an echo, the receiving antenna's job is to pick up the returning echo and shoot it along to the sensitive receiver. Here, the weak echo is amplified and sent as a voltage pulse to the indicator, so it can appear as a target pip. Basically, that's how all radars work. And in the first two pictures of this series, you saw in detail how the timer, transmitter, and receiver did their jobs. In this film, we'll see how the indicator functions. Let's take a look behind the panel and see how this typical A presentation is formed. This scope picture, as well as all others, are created by a special type of vacuum tube called a cathode ray tube. There are two basic types of cathode ray tubes, the electrostatic and the electromagnetic. These tubes produce all the scope pictures in radar. Let's see how they operate. First, to review what we know of the electrostatic tube. At the rear end of the tube is an electron gun, composed of a heater, cathode, grid, and focusing anodes. The cathode, when heated, gives off electrons, which are formed into a stream by the grid. The anodes accelerate the electrons and focus them into a beam. The beam bombards the fluorescent coating on the face of the tube and causes it to glow with a bright spot of light. These plates deflect the beam horizontally. When positive and negative voltage is applied alternately to the plates in the form of a sine wave, the beam is swung back and forth like this. But when sawtooth voltage is applied, it causes the beam to sweep across and snap back quickly. At normal speed, we get this picture, or an apparent baseline. The pips are formed by the action of the vertical deflecting plates, which bend the beam up and down each time a signal pulse is received. Thus, you can see that the electron beam is affected by both the horizontal and vertical deflecting plates. This is the usual type of A-scope. But these two sets of plates, by working together, can form any number of different scope pictures. For example, by changing the polarity of the voltage on the vertical plates, you end up with an A-scope on which the pips appear as negative deflections, like this SCR 582. These scopes, on which the target appears as a single pip, are okay for early warning and range data, but they were not designed to give elevation and azimuth data. This is why. A pulse traveling through space follows a path closely resembling that of a searchlight beam, and the greatest intensity of the beam lies in a direct line through the center. The strength of the beam diminishes gradually to either side of center until it reaches a point of minimum strength at the edges. The pattern is called a lobe, which is nothing more than an imaginary plot drawn to indicate the intensity variations of the radar beam. Let's say we have a target in the center of the beam, where the intensity is greatest. The target will reflect a strong echo, and you'll get a good-sized pip on the scope. But if the target moves ahead of the beam to a point where the intensity is weaker, the echo will also be weaker, resulting in a pip that's barely visible. As you traverse the antenna to catch up with the target, the plane is in a stronger part of the beam, and you get a stronger pip. It's the same on the other side of the beam. Minimum intensity, small pip. Maximum intensity, full pip, always letting you know when your beam is pointed directly at the target. But here's why a single pip can't provide accurate azimuth or elevation data. When the target signal on your scope fades, did the plane move ahead of the beam, behind it, above it, below it, or is the signal just fading due to a faulty set? You have no way of knowing. And if you assume the plane's getting away from you and begin searching for it, there's a 50-50 chance you'll traverse in the wrong direction and lose the target completely. To remedy the weakness of the single lobing system, we switch this single lobe back and forth so fast that you have virtually two identical lobes. When you have a target, these lobes are represented on the scope by two separate pips, one for the right lobe and one for the left. When the target is centered between the two lobes, the pips balance. That is, they're the same height. But if the target gets off-center, naturally it's going to be in a stronger part of one lobe and a weaker part of the other. Here, for instance, the target's moved to the left, so the left pip gets bigger, the right one smaller. If the target moves to the right pip gets larger. To center the target, all you have to do is traverse the antenna toward the larger pip until the two pips are again balanced. Then you know the target is centered in your beam and you're exactly on target. Keep the pips balanced and you'll stay on target. There may be times when the pips will fade because of atmospheric conditions or a maneuvering target. But although they may become smaller, as long as you keep them balanced, your beam will still be on target. In order to project this split picture on the scope, the antenna, receiver, and indicator circuits must be modified. Let's look at the antenna first. The antenna is designed so it can receive echoes alternately, first from the right lobe, then from the left. Notice, however, that each lobe is on long enough for a pulse to be sent out and its echo to return from maximum range before the next pulse is sent out through the other lobe. To handle the echoes from each lobe efficiently, to keep them from being mixed up, a special receiver circuit is used which acts like a gate. This gate allows signals from the left lobe to pass through, and then those from the right lobe. The signals go down through the receiver alternately and onto the indicator. Hold it. That's right. Before they appear on the scope, the indicator must also be prepared to receive two echo signals and display them separately. Here's how the indicator works. When a pulse was sent out through the left lobe, at the same time, part of that energy was sent over to the scope, where it began forming the baseline. Thus, when the echo from the left lobe returns, it forms the pip on that baseline. When the lobe was switched and a pulse went out through the right side, part of that energy was sent over to the indicator also and began forming another baseline, so that when the echo from that pulse returned, it formed a pip on its own baseline. So that now you have the set sending out a pulse through one lobe, waiting for an echo, then switching to the other side, sending out another pulse, and again waiting for an echo to return before switching back again. Furthermore, the echo from each lobe appears on its own baseline. Normally, the two baselines are superimposed and appear like this. But there are still two separate baselines and two pips. On the actual scope, you may see them like this, and by adjusting your spread control, you can govern the distance between them. Okay, so now you know that by switching a single lobe back and forth often enough, we can get the effect of two lobes and thus stay on target much more accurately. So far, we've only been talking about the lobes that cover the horizontal plane and measure the azimuth of a target. But when you go looking for aircraft, you need elevation data too. So for those sets, we add another lobe, a vertical one this time, to flip back and forth and supply the angular height or elevation of a target, in the same way the horizontal lobe takes care of the azimuth. Of course, the same idea holds true. Each lobe has its own pip and baseline. When the target's centered in the lobes, the pips on the elevation scope are balanced and your angular height data is correct. If the plane gains altitude, naturally it'll be in a stronger part of the upper lobe, a weaker part of the lower one. So one pip grows, the other shrinks. By turning your antenna toward the larger pip, elevating it in this case, you again balance the pips and get back on target in elevation. To sum up this business on lobes, take a look at this miniature of a pip matching radar. It has two horizontal lobes, like this, for measuring azimuth, and two vertical lobes for measuring elevation. Together, the four lobes make it possible for the radar beam to be centered on the target all the time, thus assuring you of highly accurate data. And of course, for each pair of lobes, there is a separate scope picture, one for measuring azimuth, one for measuring elevation. This type of pip matching presentation is called the K-scope. So much for measuring azimuth and elevation. You'll remember that to measure range, you need only a single pip, A-scope, and the distance from the pip to the main bang represents the range of the target. As the target approaches your set, its pip approaches the main bang. The baseline or sweep, as we've said before, represents the full range of your set. When we pick up a target somewhere within that range, it's obvious that the longer the baseline we have to represent the range, the easier it will be to read our target's position accurately, right down to the last yard. However, using a horizontal baseline, this is as long as it can be and still remain on the scope. But what we can do is stretch it out 3 times that length and put it around the edge of the scope. With this longer baseline, representing the same range that the short one did, we can read range a lot more accurately. Here's a typical circular baseline range scope, the J-scope used on the SCR 584. Now that we know why such a scope picture is desirable, let's go back to the electrostatic tube and see how we can get a circular baseline using the horizontal and vertical deflecting plates. Here's a front view of the plates. The electron beam is dead center since neither of the deflecting plates has voltage applied to it. Let's apply some and see what happens. We'll start with the deflecting plates that move the beam up and down. The sine wave represents the variation of the voltage we're going to apply with respect to time. Let's take it step by step. As the voltage climbs to this point, which we'll call A, the beam is deflected a corresponding amount toward the positive plate, upward in this case, to this point, which we'll also call A. When the voltage reaches B, its peak, the electron beam also reaches its peak on the scope, marked by B. When the voltage drops back to 0, marked by C, the beam returns to C, the center point from which it started. The same thing happens in the opposite direction. When the voltage reaches its downward peak, the beam goes down as far as it can. When the voltage returns to 0, the beam returns to center. That's one cycle of vertical deflection. Now let's look at the deflecting plates that move the beam horizontally. The same thing goes here. When the voltage reaches A, the beam moves horizontally to A. Every change in voltage produces a corresponding horizontal deflection of the beam toward or away from center. Next, let's see what happens when sine wave voltage is applied to both sets of deflecting plates. Remember that when we apply voltage to one set of deflecting plates, the electron beam is deflected upward. And if we apply the same amount of voltage to the other set of plates, the beam is deflected sideways. The combined action on both sets of plates is to move the beam along this diagonal path. To simplify the diagram, let's call the voltage applied to the vertical deflecting plates Y, and we'll label the vertical deflecting plates Y. We'll call the voltage on the horizontal plates X, and label its plates X. Now, since these voltages are going to be applied simultaneously, we can watch them more easily if we put one below the other. And to compare the movement of the voltages at any one instant, we'll put a grid over them. Let's see what happens when voltages X and Y both reach their positive peaks together. The beam is deflected to its extreme diagonal position. That's because the vertical plates are deflecting it all the way up, and the horizontal plates all the way to the side. As the two voltages complete their cycle of variation together, the beam follows a diagonal path, upwards to the left and downwards to the right. When the voltages vary together, like this, we say they are in phase. Now, let's have everything that happens to the X voltage happen half a cycle earlier than it happens to the Y voltage. When we have this half-cycle lead, we say that the voltages are 180 degrees out of phase. Let's see what will happen to the electron beam under these circumstances. When voltage Y reaches its positive peak, the beam is still deflected to its maximum upward position. However, voltage X has reached its peak in the opposite direction, causing the beam to be deflected to the right. The result is again a diagonal path, but this time from upper right to lower left. Suppose that the phase shift was only half as much, 90 degrees instead of 180 degrees. Notice now that at the starting point of the cycle, the beam is already at its maximum left position. That's because voltage X is already at its peak, while voltage Y is at zero. A quarter of a cycle later, voltage Y reaches its peak and voltage X is at zero. The beam has moved through a circular path to its maximum upward deflection. As the cycle continues, the beam continues on its curved path, forming a circle. And of course, as the action picks up to its normal operating speed, you get the illusion of a circular baseline. Remember that this circle is the end view of a stream of electrons. If we vary the phase shift, the result will be some compromise between a circle and a diagonal line, an ellipse. But phasing isn't the only thing that will affect the shape of our circle. You can have the voltages 90 degrees out of phase and still not get a circle if the amplitudes are allowed to vary. If, for example, the amplitude of voltage X becomes less than voltage Y, it will change the circle into an ellipse, pushed in on both sides, because the horizontal deflection is not as great as the vertical deflection. However, once you've corrected the amplitude, you'll again have a perfect circle. If voltage Y is smaller, you'll again get an ellipse, but one which is squashed horizontally, because the beam is not deflected to its maximum vertical position. If both voltages decrease in amplitude the same amount, the result would again be a circle, but a smaller one. When the voltage amplitudes are corrected, the circle returns to its original size. So any change in the shape or size of your circle means an improper phase or amplitude adjustment. When you've corrected the amplitude and phase, you'll end up with a perfect circle of the right size. Now you've seen how the deflecting plates can form a circular baseline. When this pattern is projected onto the face of your scope, you get a baseline almost 3 times as long as the horizontal one we started with. Now that we have our circular baseline, How are we going to produce pips on it? Both sets of deflecting plates, remember, are busy forming the baseline, so something new must be added. It's a thin metallic rod inserted in the tube from the base through the center of the screen. This is the deflecting rod that will take care of forming the target pips. Here's how it works. Let's take a look at it from the front. We'll slow the beam way down so we can explain what goes on. There. That white dot is the end of the electron beam as it strikes the face of the scope. When negative voltage is applied to the deflecting rod, the electron beam, also negative, will be repelled from the center. If we leave the negative charge on like this, the beam keeps being repelled all the way around, and as a result, we get a bigger circle. If we remove the negative charge, the beam returns to its original path. If negative voltage is applied to the deflecting rod for only an instant, the beam is repelled from the center for only an instant, and then comes back to normal. The timer synchronizes the deflecting voltages so that every time the electron beam is at top center, the transmitter is triggered. The spillover energy, picked up by the receiver and applied to the deflecting rod, causes a pip to be formed, the main bang, up at top center. This is zero range. The returning target echo voltage is also applied to the deflecting rod, and another smaller pip will be formed somewhere on the circumference of the circle. As you can see, this scope gives us everything an A-scope did: a main bang, a target pip, and a baseline along which you measure range. But because our new baseline is circular, we can make it almost 3 times as long without increasing the size of the tube, thereby giving us a more precise means of measuring range. Since our baseline is circular, to measure range, we simply put a circular range scale around the edge, with 0 at top center. By reading range clockwise to the pip, you can tell at a glance how far away the target is. Here's that same J-scope you saw earlier. It's the coarse range scope of the SCR 584 and measures ranges out to 32,000 yards. To measure range even more accurately, crank this hairline around until it's on the target pip. That makes the echo appear as an expanded pip on the fine range scope, there at the right. It's also a J-scope and shows you an enlarged 2,000-yard segment of the set's entire range. With these 2 scopes, you can locate a target to within a few yards. So much for the J-scope. There was still a need for another type of scope, but before we get into that, let's take a short break.